Here's something I need to tell you straight up, and it's gonna sound weird, but stick with me because this is the kind of thing that keeps me up at night. There's a difference between knowing something and understanding it. Like, you know your phone works, but do you actually understand the quantum mechanics that make the processor function? You know what I mean? And what I'm about to tell you about what Oppenheimer discovered is something we can know, but we will literally never be able to truly comprehend. And I'm not being dramatic here. I mean this in the most literal sense possible. Oppenheimer figured out that stars, these massive burning spheres of plasma that dwarf our entire solar system, some of them don't die the way we think death works. They don't fade out. They don't explode and scatter into space. They do something so profoundly disturbing that it breaks the rules of reality itself. They cross a threshold. And once they cross it, they're gone from our universe in a way that's more complete than any death you've ever imagined. Not destroyed, not ended, just removed from existence as we understand it. And the wild part, the part that made Oppenheimer go quiet when he realized it, is that this threshold, this limit, is something we can calculate perfectly. We can predict it to insane precision. We can write equations that describe exactly when and how it happens. But we will never, ever truly understand what it means. It's like being handed the instruction manual to reality and finding a page that just says, "Here's where the rules stop working," and there's nothing you can do about it. And if this is the kind of mind-bending stuff that makes you realize how little we actually understand about the universe we live in, hit that subscribe button right now, because what I'm about to walk you through is going to completely change how you think about death, about matter, about what it even means for something to exist. So, let me take you back to 1939, when a young physicist named Robert Oppenheimer, working with his student George Volkoff, discovered something that shouldn't be possible. They were doing calculations, just math on paper, trying to figure out what happens to stars after they die. Normal stuff for theoretical physicists, except their math kept leading them to the same impossible conclusion. Under certain conditions, a star doesn't die. It falls through reality itself. And the equation that describes this, the Oppenheimer-Volkoff limit, is one of the most beautiful and terrifying things in all of physics, because it tells us exactly where the universe stops making sense, and we can measure it. We can see it happening in space right now, but we cannot comprehend what's actually going on. That's what we're diving into today, and I'm warning you now, this is gonna mess with your head in ways you're not expecting. Here's what they teach you about stars, and honestly, it makes perfect sense on the surface. A star is basically a giant ball of hydrogen that's so massive the gravity crushes the core until fusion starts happening. Hydrogen atoms slam together so hard they fuse into helium, and that releases energy, tremendous amounts of energy, and that energy creates outward pressure that pushes back against gravity. So you've got this perfect balance, right? Gravity pulling inward, fusion pressure pushing outward, and the star just sits there burning for millions or billions of years in this stable equilibrium. Eventually, the fuel runs out, fusion stops, pressure drops, gravity wins, and the star collapses. If it's massive enough, it goes supernova, blows apart, scatters its guts across space, maybe leaves behind a neutron star or a black hole. Clean story? Makes sense. Death is death, even for stars. Except, here's the problem. And this is where Oppenheimer started realizing something was deeply wrong with this picture. When a massive star collapses, when fusion stops and gravity takes over, the compression doesn't just squeeze the star into something smaller. It squeezes it so hard that electrons get pushed into protons and they merge into neutrons. The entire star becomes one giant atomic nucleus made of nothing but neutrons packed so tight that a teaspoon of this material would weigh about 1 billion tons. 1 billion tons. In a teaspoon. That's a neutron star. And we've observed hundreds of them in space, and they're real and they exist, and that's already insane. But stay with me, because here's where it gets absolutely bonkers. Oppenheimer did the math on how much mass one of these neutron stars could actually hold before the neutrons themselves couldn't resist gravity anymore. And what he found was a hard limit. A specific mass, approximately 2.17 solar masses, give or take depending on the equation of state of neutron degenerate matter, which we still don't fully understand, but somewhere around 2 to 3 times the mass of our Sun. Below that limit, neutron degeneracy pressure, which is a quantum mechanical effect where neutrons resist being in the same space, can hold the star up against gravity. Above that limit, nothing can. And this is where Oppenheimer's math led him to something that sounds like science fiction, but is just physics. Above the Oppenheimer-Volkoff limit, there is no known force in the universe that can stop the collapse. The star doesn't explode. It doesn't scatter. It keeps falling. And it falls through every possible state of matter we understand, until it reaches a point where space-time itself breaks down. It becomes a black hole. But here's the part that actually disturbed Oppenheimer and his colleagues when they first worked this out, the part that still disturbs physicists today. They could calculate exactly when this happens. They could predict it, but they could not, and still cannot explain what it means for matter to do this. What does it mean for something to fall through reality? What does it mean for space and time to break down? These aren't rhetorical questions. These are actual gaps in our understanding that the math points to but cannot cross. Picture this, and I want you to really try to visualize what I'm describing, because this is one of those things that sounds abstract until you actually imagine it, step by step. You're standing next to a neutron star, which obviously would kill you instantly, but ignore that for now. This is a thought experiment. This thing is maybe 20 kilometers across, about the size of a city, but it weighs more than our entire sun. You drop a rock onto its surface. That rock accelerates so fast it hits the surface at something like 1/3 the speed of light. 1/3 of 186,000 miles per second. The impact releases more energy than a nuclear bomb. That's how strong the gravity is. Now imagine this neutron star has exactly the Oppenheimer-Volkoff limit worth of mass. It's right at the edge. Balanced. Now imagine you could add just a tiny bit more mass. Maybe another moon's worth of material falls onto it from space. Just a little push over the limit. And then something happens that defies description. The neutrons that were holding the star up, resisting compression through quantum degeneracy pressure, they can't anymore. There's too much mass, too much gravity, and the whole thing, all 2 or 3 solar masses of neutron degenerate matter, starts falling inward. But here's where your brain should start hurting. Falling inward to where? The star is already compressed to the point where neutrons are touching each other. There's no empty space, no room to fall into, but it falls anyway. It falls through the quantum foam of space-time itself. And as it falls, something happens that we can describe mathematically but cannot visualize. The curvature of space-time becomes so extreme that time itself starts to break down. From the perspective of someone watching from far away, the star appears to slow down as it approaches what we call the event horizon, the point of no return. It gets redder and redder as light gets stretched by gravity, and it appears to freeze right at the edge, never quite crossing over. But from the perspective of the matter falling in, if matter even has a perspective at this point, which is questionable, there's no freezing. It crosses the horizon and keeps falling, and falls forever in a finite amount of its own time, which doesn't make sense, but that's what the math says. And here's the thought experiment that really illustrates how broken this gets. Imagine you had a magical clock made of indestructible material, and you dropped it into this collapsing star as it crosses the Oppenheimer-Volkoff limit and becomes a black hole. From outside, you'd see the clock tick slower and slower and slower until it appears to stop completely right at the event horizon. But if you could somehow ride along with the clock, your clock would keep ticking normally, and you'd fall right through the horizon and not even notice the moment you crossed it. And then you'd keep falling toward the center, toward what's called the singularity, and all our physics equations that describe what happens next literally divide by zero and break. They don't give impossible answers. They don't give wrong answers. They give no answers. The math itself stops working. And Oppenheimer knew this. He calculated it in 1939. He showed that above a certain mass, physics as we understand it reaches a boundary where it cannot see past. This is what I mean when I say we can know it but never comprehend it. We know it happens. We've observed black holes. We've measured their masses. We've seen stars collapse. But what it means for matter to do this, what actually happens at the singularity, what it means for space-time to have a boundary beyond which our equations fail, we cannot comprehend this in any meaningful way. It's not like we're missing a piece of the puzzle. It's like we've found the edge of the puzzle and discovered the table it's sitting on is an illusion. Now, let me tell you about Oppenheimer's reaction when he and Volkoff first worked through these calculations, because this is where it gets personal and human. They published their paper in 1939, just months before World War II started consuming everyone's attention. The paper was called On Massive Neutron Cores, and it's this dry academic thing full of equations and tensor calculus, and it's technically brilliant, but what's not in the paper is what Oppenheimer reportedly said to colleagues around that time. He understood that he'd found something disturbing, a place where physics ends. And for a physicist, especially one as philosophically minded as Oppenheimer, who read Sanskrit and studied ancient texts about the nature of reality, finding the edge of knowability was existentially troubling. He knew that above approximately 2 solar masses, maybe 3, depending on assumptions about neutron star composition, which we still argue about today, a star crosses a threshold from which there is no return and no understanding. It doesn't become something else. It becomes a question mark, a hole in reality where our comprehension fails. And while you're processing that, while you're sitting there trying to wrap your head around the idea that there are things in our universe we can measure, but never truly understand, drop a comment and tell me what city or country you're watching from. I'm always curious where in the world people are who want to know about this stuff, who aren't satisfied with easy answers, who want to know what's really going on even when the answer is we can't know. So comment below. Let me know where you are. Okay, so back to this limit, this boundary in reality that Oppenheimer discovered. Let me give you some actual numbers, because this is where it gets specific, and the specificity makes it more disturbing, not less. The Oppenheimer-Volkoff limit, as calculated in their original 1939 paper, came out to about 0.7 solar masses. But that calculation made certain assumptions about how neutrons behave under extreme pressure, and it turns out those assumptions were too simple. Modern calculations, using more sophisticated equations of state for neutron matter, using data from particle accelerators where we slam nuclei together to see how nuclear matter behaves at high densities, those calculations put the limit somewhere between 2.17 and 3 solar masses, depending on exactly how stiff or soft neutron matter is under pressure. We don't know the exact number because we can't recreate neutron star conditions in a lab. We can't compress matter that hard on Earth, but we know the limit exists, and we know it's somewhere in that range, and here's the kicker, we've observed it in nature. There's a neutron star called PSR J0348+0432, and yes, I know that's a terrible name. Astronomers are not creative with names, but this thing is special. We've measured its mass using timing data from its pulses, and it comes in at about 2.01 solar masses, right near the limit. We've observed other neutron stars with similar masses. The heaviest confirmed neutron star we've found is PSR J0740+6620 at about 2.14 solar masses. Right at the edge, and here's what this means. Somewhere between 2 and 3 solar masses, there is a line. On one side, you get a neutron star, something we can observe and measure and study. On the other side, you get a black hole, something that removes itself from observable reality. And we don't know exactly where that line is because we don't fully understand how neutron matter behaves at these densities. But we know the line exists because we've never found a neutron star heavier than about 2.14 solar masses, and we've never found a black hole lighter than about 5 solar masses. There's a gap, a range where we don't see anything because anything in that range either hasn't formed yet or can't exist stably. And this gap is evidence of the limit Oppenheimer calculated. It's evidence that there's a threshold in nature beyond which one set of rules stops and another begins. Now here's the deeply disturbing part that Oppenheimer understood, and that most people don't think about. When a star crosses this limit and becomes a black hole, the matter doesn't disappear. It's still there. All those neutrons, all that mass, it's still affecting space-time through gravity. We can detect black holes because they pull on things around them. But the matter itself, what it becomes, where it goes, we cannot know. Not because we don't have good enough telescopes, not because we haven't done the right experiments, but because the structure of space-time itself prevents information from escaping once it crosses the event horizon. This isn't a technological limitation. It's a fundamental limit built into reality. When Oppenheimer realized this, when he understood that his equations were pointing to a place in nature where knowledge itself has a boundary, he had to sit with the philosophical implications. And later, after he led the Manhattan Project and saw what happened at Hiroshima and Nagasaki, after he watched cities vanish in nuclear fire, after he quoted the Bhagavad Gita saying, "Now I am become death, the destroyer of worlds," I think this earlier discovery about limits in nature must have haunted him differently. He'd found a limit in physics where comprehension ends, and then he'd found a limit in human ethics where his own choices ended in mass death. Two different kinds of limits. Two different kinds of not being able to go back. Two different kinds of crossing a threshold from which there is no return. And this is where we need to talk about what this means for you, sitting there right now, made of the same matter that obeys these same laws, existing in the same universe where these limits exist. Because this isn't just abstract physics happening in distant space. This is about the nature of reality itself and your place in it. Every atom in your body, right now, has a theoretical limit. If you could somehow compress all the atoms in your body, squeeze them down through electron degeneracy pressure, through neutron degeneracy pressure, keep squeezing past the Oppenheimer-Volkoff limit, your matter would fall through reality the same way a massive star does. It would cross the threshold and become unknowable. Now, obviously, this isn't going to happen to you because you're not 2 solar masses and you're not under that kind of gravitational pressure. But the point is, the rules that apply to collapsing stars apply to you too, because you're made of the same stuff. You exist in the same universe with the same limits. And here's what that means. You are patterns of matter that physics allows to exist in an observable state. But the same physics that allows you to exist also contains within it the instructions for how matter can remove itself from observation, how it can cross a line beyond which reality as we experience it stops making sense. You're not separate from this. You're part of it. And here's something else Oppenheimer understood that most people don't think about. The universe is full of black holes. We estimate there are maybe 100 million stellar mass black holes in our galaxy alone. 100 million places where matter has crossed the Oppenheimer-Volkoff limit and fallen through reality. 100 million holes in space-time where information goes to die. And at the center of our galaxy, there's a supermassive black hole called Sagittarius, a star that weighs about 4 million solar masses. 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. That thing is there right now, 26,000 light-years away, warping space-time so severely that nothing can escape if it gets too close. And we orbit around it. Our entire solar system, our Sun, our planet, you sitting there watching this. We're all orbiting a cosmic drain that we will never understand. And the crazy thing is that this should terrify us more than it does. We've built a civilization on a rock flying through space around a star that's part of a galaxy that orbits a supermassive black hole. And we just go about our daily lives like this is normal, like this is fine. But Oppenheimer couldn't ignore it. Once he understood what the math was telling him, once he realized that there are limits built into the fabric of reality beyond which knowledge itself cannot go, he couldn't unsee it. It changed him. You can see it in his later writings, in his lectures after the war. He talks about the limits of human understanding, about how science reveals both what we can know and what we cannot know, about how discovering the boundaries of knowledge is as important as discovering new knowledge. And I think finding the Oppenheimer-Volkoff limit early in his career, finding this hard edge in physics where equations break down and comprehension fails, I think that shaped how he saw everything else, including the bomb, including what humans are capable of, including the limits of our own wisdom. Because here's the thing about limits. Once you find one, once you discover that there's a place where the rules stop working, you start wondering if there are other limits you haven't found yet. Limits to human knowledge, limits to human control, limits to how much we can understand about what we're doing. And Oppenheimer found a lot of limits. The Oppenheimer-Volkoff limit in neutron stars. The limit of how much energy you can extract from uranium before it explodes. The limit of his own ability to control what happened after he helped create the atomic bomb. And in every case, the limit was something you could calculate, something you could see coming, but something you couldn't stop once you crossed it. That's the pattern. That's what haunted him. The knowledge that some thresholds are one-way doors. You can predict them. You can measure them. But you cannot comprehend what's on the other side until you've already crossed over, and by then, it's too late to go back. So let's bring this home, and let me tell you why this matters beyond just physics trivia or Oppenheimer history. What he discovered about stars is a metaphor for something deeper about the universe we live in. Reality has boundaries, not boundaries in space, boundaries in comprehension. Places where our best equations, our most sophisticated mathematics, our deepest understanding all point to the same conclusion, which is, beyond this point, we cannot know. The Oppenheimer-Volkoff limit is one of those boundaries. It tells us exactly how massive a neutron star can be before it crosses into black hole territory, before it falls through the floor of reality. We can calculate it. 2 to 3 solar masses depending on the equation of state of neutron matter. We can observe it. We see neutron stars clustering below that mass and black holes clustering above it. We can predict it. We know that any star remnant above that limit will collapse, but we cannot comprehend what happens at the singularity inside a black hole. We cannot visualize what it means for space-time to curve infinitely. We cannot understand what happens to information that falls past the event horizon. And this isn't a failure of imagination. It's a fundamental limit in the structure of reality itself. Oppenheimer found that limit in 1939, working with George Volkoff, doing calculations on paper with pencil and math. And what he found was beautiful and terrible in equal measure. Beautiful because the math works. Because you can derive this limit from first principles using general relativity and quantum mechanics, and it all fits together coherently. Terrible because the coherent math points to incoherence. It points to a place where the universe hides information from itself, where matter can exist in a state we cannot observe or understand. And once you know this, once you really sit with the implications, it changes how you see everything. That table you're sitting at, that phone in your hand, the ground beneath your feet, all of it is matter that obeys the same rules that create black holes. All of it could, in principle, be compressed past the Oppenheimer-Volkoff limit and fall through reality. It won't happen because you don't have a neutron star's worth of gravity squeezing you, but the potential is there, written into the laws of physics. You exist in a universe where matter can remove itself from comprehension, where there are doors that only open one way, where some questions cannot be answered, not because we're too dumb or we don't have good enough technology, but because the questions themselves point past the boundary of knowable reality. And Oppenheimer saw this coming. Not just in neutron stars, but in nuclear weapons too. He helped create something that crossed a limit, a threshold where human capability exceeded human wisdom, where we gained the power to destroy ourselves before we gained the understanding of how to handle that power responsibly. The Oppenheimer-Volkoff limit in stars, the critical mass limit in uranium, the limit of human restraint when given godlike power. All limits, all thresholds, all one-way doors, and all predicted by math that we understand but cannot fully comprehend the implications of until it's too late. So next time you look up at the night sky, remember that scattered among those stars are objects that have crossed the limit Oppenheimer calculated. Objects that were once stars like our sun, but accumulated too much mass and fell through reality. Objects that now exist in a state we can detect but never understand. Holes in space-time where the rules break down. And remember that the same physics that creates those cosmic monsters also creates you. You're made of matter that obeys the same limits. You exist in the same universe with the same boundaries. The same fundamental truth that some things can be known but never comprehended. Oppenheimer knew this. He calculated it. He saw it in equations. And later he saw it in mushroom clouds and radiation burns and cities turned to ash. He saw limits everywhere. And he saw that the most dangerous limits are the ones we can predict but cannot stop ourselves from crossing. Can you look at the universe the same way, after knowing there are things in it we can measure perfectly but will never truly understand? If this video just shifted your entire perspective on what it means to exist in a reality with hard boundaries on knowledge itself, smash that like button so I know you want more of this mind-bending physics. And subscribe right now because I'm diving into more of Oppenheimer's discoveries that reveal the hidden structure of reality, the limits we're approaching, the thresholds we're about to cross. Hit that bell so you don't miss when I explain what Oppenheimer discovered about antimatter that almost nobody talks about, or when I break down his calculations on stellar collapse that predicted things we're only now confirming with gravitational wave detectors. Comment below which Oppenheimer discovery you want me to explore next. Thanks for watching.